Hello, my name is Zhenis Buldirshin. I'm a student group 4. iOS number 1 with function of state with specific values of physical quantity and linear and Hermitian operators. And the plan, the first is the introduction, the next is a wave function of state with specific values of physical quantity, linear and Hermitian operators, and the conclusion. The first is introduction. Introduction in quantum mechanics of quantum physics, a wave function, a mathematical description of a quantum store of an isolated quantum system. And a wave function is a complex valued probability amplitude and the probabilities for the possible result of measurements made of system can be derived from its some maximal set of common observations. And all these wave equations are enduring importance. The Schlesinger equation or Pauli equation are under many circumstances excellent approximation of the relativistic variation, and they are considerably easier to solve in practical problems, the relativistic counterparts. The first is the Klein-Gordon equation and the Dirac equation. While being relativistic, do not represent full reconciliation of quantum mechanics and special relativity. And the next is the relativity makes inevitable that the number of particles in a system is not constant. And for full recognition, the quantum field theory is needed. And in this theory, the wave equation and the wave function have their place, but in some different ways. The first topic is the wave function of state with specific values of physical quantity. The wave function is a mathematical description of the quantum state. So wave function of state with specific values. In quantum physics, a wave function is a mathematical description of quantum state of a particle as a function of momentum, time, position, and spin. And the symbol used for wave function is a Greek letter called. And in this picture, by using a wave function, the probability of finding an electron within the matter wave can be explained. And this can be obtained by including an imaginary number that is squared to get a real number solution, resulting in the position of an electron. And the concept of wave function was introduced in the year 1925 with the help of the Schlesinger equation. And in this picture we see the graph of the functions. The next the proportions of wave functions. The first is all measurable information about the particle is available and should be continuous in the symbol as single valued. And using the Schlesinger equation, energy calculates becomes easy, and probability distribution in 3 dimensions is established using the wave functions, and the probability of finding particle if it exists is number 1. And wave function of state with specific values. A clue to the physical meaning of the wave functions, this symbol xt is provided by the two-slit interference or monochromatic light. In this picture we see the monochromatic light, wavelength lambda, and that behave as electromagnetic waves. The wave function of a light wave is given ext, and its energy density is given by E squared, where E is the electric field strength, and the energy of an individual photon depends only on the frequency of light. So A photon equal to the HF. So A square is proportional to the number of photons, and when light waves from C1 interference with light waves C2 and the viewing screen in distance dA, and the interference pattern is produced, and the bright fringe is corresponding to points of appearance of screen. So the next is a wave function of state with specific values. Suppose the screen is initially exposed to light. If the screen to very weak light, the interference pattern appears gradually. In this picture, we see the interference pattern build up gradually under low intensity left to right, and individual photon hits on the screen appear as dots, and the node density is extended to be large at locations where the interference pattern will be ultimately the most intense, and in other words, the probability that a single photon will strike a particular spot on the screen and is proportional to the square of the total energy field, E square, and that points. And under the right conditions, the same interference pattern develops for matter particles such as electrons. In this picture, we see the interference patterns. The first picture, the second picture is gradually under low intensity light. The next is linear and Hermitian operators. So the first is a linear apparatus. Function f is called a linear apparatus if it has two proportions. The first is fx plus y equal to the fx plus fy for all x and y, and fcx equal to the cfx for all x and L constant c. It follows that fax plus by equal to the afx plus bfy for all x and y and all constants a and b. And the most common example of linear apparatus during school musical and differential and integration, when the above looks like that: d divided dx and times au plus bv equal to the a du divided dx plus b dv divided dx, and the u and v are the functions over x, and the ab are constants, and the r and s are the limits of integration. And linear operators in the functions are the maps of one vector on other vectors. They can be represented by matrices, which can be thought of as coordinate separation of linear operators. The 4 and nx and a matrix is an example of linear operators. The next is Hermitian operators, and physical variable must have real expansion values and eigenvalues. The impulse that the operators expressing physical variables have some spatial properties. So by converting the complex conjugate of expansion value of physical variable, we can easily show that physical operators and their of Hermitian object. In this picture, we see the apparatus that say our Hermitian are called Hermitian apparatus, and in the symbol it's apparatus. The next is a conclusion. So the concept of function space enters naturally in the discussion about the wave function, and the function space as a set of functions usually use some defining requirements of the functions, and in the present case that they are square integrable, sometimes with an algebraic structure of the set, in the present case of vector space structure with the inner product. So together with a topology in the set, the latter will sparsely be used here. It is only needed to obtain a precise definition of what it means for a subset of a function space to be closed. This observation is a foundation fundamental formation of quantum mechanics. There are many types of important operators of quantum mechanics. In this lecture, we present some of these as a unitary operators that determine the time of Henle operators, which can be assigned to physical observation proportions of a system, such as momentum of energy. And we will also discuss how we manipulate operators and combine them in variable ways. That's all. Thank you for attractions.